is expected of a Hamiltonian is the total energy of a system is always a constant. Okay? And alpha and beta are related to each other just like our A and B in the linear atomic chain case. And finally, you can write this in terms of one of the two unknowns only. Okay? And then this actually is a constant. Because for a traveling wave, it's something of that form. Now again, you make the jump and say that, well, if I write alpha in terms of P and Q, just like what I did before, okay, P and Q, the in-phase and quadrature term, because I can write this in terms of in-phase and quadrature terms, then my Hamiltonian for classical electromagnetics is just equal to that. Okay? Now these are functions of time, and this looks exactly like a classical harmonic oscillator. I make a leap and say that when I study a classical harmonic oscillator, I can see this connection. And see this connection and hence elevate all this to quantum harmonic oscillator. And that should be the Hamiltonian for a quantum harmonic oscillator. And it goes the same algebra as I did before for the linear atomic chain. Okay? I do the same algebra as I did before for the linear atomic chain. And then I can write P hat equals to minus I H bar d dq kind of thing. Q hat equal to Q, and then do change of variables like I did before. Okay, then finally I have the quantum harmonic Hamiltonian, the Hamiltonian for the quantum harmonic oscillator to be something of that form, which also can be written as this. Plus R. Okay? So, I can also say that classically, the classical Hamiltonian can be written in this manner, okay, can be written in that manner. I can also write the classical Hamiltonian as omega over 4 if it's something of this form, alpha t, alpha conjugate t, plus alpha t, alpha conjugate t. And then I elevate this to a quantum Hamiltonian, it should be alpha over 4, alpha hat, alpha dagger hat, plus alpha hat, dagger. Okay, if I elevate them, and then I can make comparison between these two. I can make comparison between these two and say that my alpha hat must be equal to 2h bar a hat. Okay, my alpha hat must be equal to 2h bar a hat. And then when I have a traveling wave solution now, I can write this traveling wave solution in terms of a field operator rather than in terms of a scalar field. So the field will be elevated to the operators. Okay, EZ becomes something like h bar omega k for the particular k number. Okay, omega is associated with the wavelength of the wave that travels in the system, so we can associate omega with k. And then this amplitude can become an operator, okay? And then you will have this may look something like that. And then you can convert this into Heisenberg picture and put the time dependence out explicitly as well, plus its complex conjugate. So the field now becomes an operator. And then you can write down the magnetic field as well. Okay, magnetic field now also becomes an operator. Actually with the same factor over here, plus 1 over c, okay, depot factor, times ak hat, and then with the same factor, e to the I kx minus I omega kt, plus its complex conjugation. So all the fields now become operator, just like the case of linear atomic chain. Okay? And you can generalize this to a 3D plane wave. In the case of a 3D plane wave, you say if you go through the same exercise, or just do it for an arbitrarily polarized plane wave, and if the plane wave travels to the medium, it will be something like this. And also, right now I also only assume one plane wave mode that is propagating through space. What happens if I plane wave with different k vectors? So I can actually generalize this to a plane wave with arbitrary k vectors that in general E hat, the field operator is sum of plane wave propagating in all directions and then different polarizations times an amplitude which is given by this if you work it out properly for 3D waves, okay, times the vector E sub s, this is a classical vector, times a annihilation operator that's a function of k, okay, that also is a function of s being the polarization. Okay, this is the polarization. Okay, and then times a plane wave. The plane wave can be written as k dot r, and then omega and k are related in that manner. Okay, plus is complex quantization. This is a typical electromagnetic field propagating through vacuum when it's quantized. And the polarization can be horizontal or vertical polarization. It can be left circular polarization or right circular polarization. But it doesn't matter what you put here. And then the B would be equal to different plane wave modes, h bar omega k over 2b epsilon naught, 1 over c. And then when you take the curl of E to get B, you have this k hat cross ES. E to the I k dot r minus I omega k t plus complex conjugation. Okay, so these are the quantized form of the electromagnetic field. But you should treat them as operators, because they are not fields yet. In order to find fields, what must you do again? You find the quantum state that you are in and take the expectation value of this operator with respect to that quantum state. Okay? Take expectation value of this. And then the Hamiltonian for this system is actually the Hamiltonians over all possible k values.
Is that k hash
Which is that?
the k?
Oh, this is a unit vector, I'm sorry. This denotes unit vector. Okay, unit vector. And if you take the curl of E, you get a k vector pointing in the k direction, and that should give you a unit vector, if I'm correct. I think I'm correct. Okay, I can go back to check if it should be a unit vector, or should it just be a k vector?
So it's kx,
Hmm?
k for cross product, yes.
Yeah. If I plug into Maxwell's equation, say if I plug into Maxwell's equation that looks something like this, take the curl of E, you get B. I take the curl of that k, and then I take the time derivative, and then I can have I omega something. I have to see that. I'll go back and check if this should be k hat or k vector. Okay? That's a good point. Okay, and are there any questions regarding this quantization of the electromagnetic field? And what you notice is that if you take the expectation value with respect to the photon number state, okay, say if you are in a photon number state that describes this creation operator, for say particular k, you will have different modes, okay, with different polarization. Okay, this always becomes 0. because NKS, AKS, NKS is always equal to 0. Because this will lower this by 1, and when you take the inner product between them, they're always 0. So these are known as non-classical states. Okay, this are known as non-classical. Because they actually give you 0 expectation value when you take them against these field operators. You will have to actually think of other kinds of states, other kinds of quantum states in order to match up with the classical state. We'll talk about those states later on. Okay. Let's see. So what happens then is that a Hamiltonian for a multi-mode case will consist of the sum over the modes and the polarization. The Hamiltonian for the single mode and single polarization case, you will have to sum over all this to get the multi-mode Hamiltonian. And in general, the Hamiltonian will look something like this. Okay. Omega will depend on K, your plane wave mode, and then the annihilation and creation operator will also depend on K and the polarization. Polarization just denote whether you're with the horizontal polarized case or the vertical polarized case. And then you will have a half case. And this is the Hamiltonian for a general electromagnetic system in vacuum. And it will look something like that. Okay. So this is like sum of different Hamiltonians. Okay, different Hamiltonians with different K vectors. And if you have sum of Hamiltonians, then you should define the quantum state as products of, you can define the state as, say if you have been wave number K1, you have this number states in K1 times wave number K2 times this, and these are called product state. Because these are sums of Hamiltonians. Okay, each Hamiltonian has its own eigenstate. Okay, each of these Hamiltonians, if you look at this one, if you were to fix K and look at this is its own eigenvalue and eigenstate. Okay, the eigenstate of that we can call this. The eigenstate of the second case we can call this. The eigenstate of the third case we can call this. And these are called the product state. Okay, these are the product state, and they become the eigenstate of the sum of Hamiltonians. Okay, just like if I have A1 psi 1 is equal to E1 psi 1, and then A2 psi 2 is equal to E2 psi 2. And these are two different operators, and if they have a system A1, A2, then I should use psi 1 and psi 2 to describe this system, the product state. Okay, it's maybe some new eigenvalue, psi 1, psi 2. Okay, something like that. So you have to take products of this eigenstate to form a new state, and those are called the Fock states. Okay, these are called the Fock states. And I'll talk about this more in the next lecture. And then we continue next time since I'm running out of time. Okay, are there any questions regarding this?
What is E? What's E?
E is the,
Sum of E1
in this case, if these two systems are uncoupled, E will be just E1 and E2. Okay, E1 and E2. Because A1 will operate on psi 1, A2 operates on psi 2, you will just produce E1 and E2. Okay, we stop here.